let's see what will happen if I have a mixed combination of batteries, right? Let's say I have n batteries in series and m such combinations of n batteries in series in parallel, right? Right. M, I would write branches in parallel. So let's say there are n such batteries in series and there are m such branches in parallel, right? Okay. So let's see what will happen in this case. I can write the R equivalent as n into R by n, right? That is pretty intuitive. Now, the equivalent EMF will be n equivalent. Why? Because each of these n batteries in series will give me an equivalent EMF of n epsilon, right? Where epsilon is the EMF of one battery, right? And all of these batteries are going to have some internal resistance also. Now, what happens is, once I have the potential across these 2 points, it will be same across any 2 points. That is the principle of a combination in parallel, right? So yeah, so I can write I or current as potential upon resistance. Now to this combination, I'll obviously be connecting an external resistance, right? Otherwise, what is the use of my circuits? This is the resistance in series. So I can write the total effective resistance as R plus NR by M. Right, so if I simplify this, I will obtain Mn into epsilon upon M into capital R plus N into small r. Now if I want to maximize this current, right, this is the current flowing through this entire setup. If I want to maximize the current, then I need to minimize the denominator, right? This formula is important. I need to minimize for I to be maximized, MR plus NR should be minimum. So R I get as NR by M. So if I know the internal resistances and the external resistance, I can find the ratio of N and M so that I obtain maximum current from this circuit. This is important and must be remembered. Right, now we come to a very important principle in this chapter called the superposition principle. Right, now see, suppose I have a resistance and in the circuit I have 2 cells, 2 batteries, right, this way. Now to find the effect, let's say current, right, what I can do is I can consider one battery, consider that this battery is not present, and then calculate the effect of the first battery or the current due to the first battery, and in the second case I'm going to consider this battery, make it 0 and find out the current due to the second battery and just add them together. So superposition principle is nothing but adding up effects by taking one source at a time. Right. Now, next we move on to another very important concept called the Kirchhoff's rule. Right? It's very easy to apply. We just need to remember the sign conventions, which are quite important. Now, here in this chapter, we're going to study 3 very important rules. One is the superposition principle, the second is the Kirchhoff's rule, and the third is the loop or voltage rule. So let's see the Kirchhoff's rule first. It is also called junction or current rule. Right. So if I have a junction where, let's say, 4 currents are passing, right? These are coming in and this is going out. There can be any combination. Then I will use charge conservation. Now per unit time also charge should be conserved. So basically I'm going to use the current should be conserved, right? So the amount of current which is coming in at the junction, at any point of time should be equal to the amount of current going out. This is extremely important, right? It can help us simplify problems, solve them. So yeah, these should be remembered. Then we come to loop voltage rule. Most important, right? Let's see what that is. Now, the first important point is let's start with the circuit to understand things better. Let's say it's a battery, another resistance, another battery, and yeah. Now, let's say this is R1, this is R2, this is V1, and this is V2. Right? Now, first I need to choose a direction in which I'm going to traverse this circuit, and then the convention. Now, what does it say? The voltage, the total voltage across a loop, a closed loop, total voltage across a loop should be 0. That's it. Now, if I choose a direction, let's say clockwise, suppose I decide to move in this direction, then I will move throughout the loop, calculate the voltage changes across each element in the circuit and equate it to 0, because that is the total voltage drop in the loop, which I know should be 0. Now, these conventions are very important, which I'm going to discuss now. When I'm moving through a resistance, if I move in the same direction as the current passing through it, then the voltage will drop, so I will take a negative sign with the voltage. And when I'm passing through a battery, so when I move from plus to minus, the voltage will be negative. And when I move to minus to plus, there will be voltage gain. So in the equation, I'm going to take it as positive. Let's see how I'm going to use the loop voltage rule in a circuit. Moved on to the next page. So yeah, this is a battery. There is a resistance. There is another battery. This is V1, this is V2, this is R2, and this is R1. This is the direction that I've chosen. Right, so let's start. Suppose I move across the loop and the current is going in this direction. So I know that, fine, I am moving, when I move across this R1, then I'm moving in the direction of current. So what will happen is, I can easily write the voltage drop across R1, right? It will be I into R. Right, so let's say the current is I1, so I can across it will be I1 R1, the voltage drop. Now, since I'm moving in the direction of current, I will take the voltage change to be negative. Okay, since here I'm moving from plus to minus in the battery, I'm going to take the voltage drop as voltage change as negative. Here again I'm moving in the direction of current, so again it will be negative. But here I'll be moving from minus to plus. So here the voltage change will be positive. So when I write all these, the voltage change across this, all these 4 components with the correct sign conventions and equate and add them up. The sign convention is very important. If I add all these voltage drops and gains up, the sum should be 0. So that is the voltage, loop voltage rule. Now we'll see the application of this rule in the questions which are going to follow. Next we come to energy and power. So work done we know will be charge into potential, which is V into I into T. Because if I'm moving Q charge across V potential, the work done will be Q into V. And V as in Q I can write as I into T, because current is nothing but charge moved per unit time. Now power is work done per unit time. So this will be V into I, which I can also write as V squared by R or I squared R. Now this power is released as heat. So heat released can be written as I square RT. Right. Now if I talk about maximum power transfer, suppose I have this circuit where this is a cell of EMF psilon, this is the internal resistance of the cell, this is the external resistance, then power can be written as epsilon square R upon R plus R whole square, because it is given by I square R, right? Now, if I write dP by dR is equals to 0, because I need to maximize the power. So this is how we maximize a variable. So if I maximize this, substitute this from the equation of power from here and then solve this derivative, then I will obtain R is equals to R. So I know that in such a circuit, when internal resistance is equals to external resistance, maximum power transfer is going to take. Now we come to electric measurement, right? So galvanometer and ammeter, they measure current, and voltmeter, as the name suggests, measures voltage, right? Galvanometer can measure very small amount of currents, right? So when I need an ammeter, how am I going to obtain an ammeter from a galvanometer? Let's see. So I'll talk about the ammeter first. So what happens is, if I take a galvanometer and connect a resistance called the shunt resistance in parallel with it, then what will happen is that, suppose Ig plus I current is passing through it, and here Ig current passes through the galvanometer and I current passes here. Now see, galvanometer can allow only a very small amount of current to pass through it. So that's why I want to shift the direction of current to somewhere else. So I connect the resistance in parallel, right? So yeah, so I max here is Ig plus I. Now this entire setup can measure a much higher current than Ig, because we are effectively somehow making sure that still a very small amount of current passes through the galvanometer, but we can measure a larger amount of current, right? So yeah, and in this case, Ig Rg by voltage loop rule will be equal to I into Rs. Right, so this is a very simple combination. Now, if I want to get a voltmeter from a galvanometer, what am I going to do? I'm going to take a galvanometer and put a resistance R in series with it. Why? Suppose galvanometer has a resistance of Rg. Now Ig amount of current is passing through it, and I want to keep Ig as low as possible, but I want to be able to measure higher voltages also. So I will simply put a resistance R, which is going to increase the voltage across the 2 points, but Ig will be less because I have added another resistance, and more the resistance, lesser will be the current, obviously. So V max that can be measured by it is Ig into Rg plus R. We are going to talk about the Wheatstone bridge now. Now, suppose I have a circuit which is something like this. This is another resistance and another resistance, and this is a denominator. And I have 2 points A and B. This is the voltage V, R1, R2, R3, and R4 are the resistances. If I talk about the potential across A and B, and I follow this path, then I will get, this will be equal to V into R1 upon R1 plus R3. And if I follow this path and find out the potential AB, this will be V into R2 upon R2 plus R4. Now, if I want no current to pass through these 2 points, this is the potential at B, the potential at A. If I want zero current to pass through these 2 points, then I can simply equate these two potentials, and which will fetch me this equation. And this is the equation for a balanced Wheatstone bridge, right? R1 upon R3 should be equal to R2 upon R4, and this we need to memorize. which is very simple. Left hand side, the two resistors on the left hand side, R1 upon R3, their ratio should be equal to R2 upon R4, which is the condition for a balanced Wheatstone bridge. Right, and yeah. Now we'll talk about RC circuits. Right, let's move on to RC circuits, which constitute a very important section of this chapter. First, I'm going to talk about a capacitor. What is a capacitor? A capacitor, we all know, can store charge, right? So, how the symbol for a capacitor is this. They are represented like this in a circuit, two equal parallel lines. Okay, and right. So, capacitance is defined as C, which is equals to the charge stored by it per unit potential drop, right? So V is equals to Q by C. This is a very basic equation of a capacitor. Whenever we talk about a capacitor, its capacitance will be given, right? As in, it'll have a specific capacitance. Right. Now, in a circuit, if we talk about charging of a capacitor, the capacitance of C, resistance of R, E, and I. Suppose the capacitor is being charged. We'll talk about charging first, right? So I can write the equation, simply apply the loop rule and write an equation for potential drops across all the three components E, R, and C, and write this equation Q by C from here, right, plus I into R, because I'm moving along the current, right, and it is being charged, so I can write Q by C, minus E, because I'm moving from minus to plus here, minus E is equals to 0, and I can substitute as dQ by dt, right? We studied that in the first part of the chapter. Now, if I substitute this over here, I can easily get this equation dQ upon EC minus Q is equals to dt by RC. If I solve this, I will get Q is equals to EC into 1 minus e raised to the minus t by RC. So this is the relation between charge on a capacitor with time, and this is, we should remember, this is only applicable if at time t is equals to 0, the charge on the capacitor was 0. And here R into C, the resistance value and the capacitance value, their multiplication is called tau, which is called the time constant of the circuit, of the RC circuit. Right? Now, from this equation, we can see that as t tends to infinity, Q will tend to EC, which is also Q max. This is the maximum charge a capacitor of capacitance C can store when connected to an RC circuit with EMF E. Current can be written as dQ by dt. So current across the capacitor will be this, right? So I can write this as Q max upon RC into e raised to the minus t by RC, because Q max is EC. So in the equation, I can write the equation for Q as Q is equals to Q max into 1 minus e raised to the minus t by tau, right, or t by RC. Right. So now I can write this equation as E by R into e raised to the minus t by RC. This is the equation for the current across a capacitor. And I max, I know, I can denote as E by R. Right. Now, at the starting of charging, this is again important. Potential across the capacitor is 0 and current across it is non-zero, and at the ending of charging, current across the capacitor is 0 and voltage across the capacitor is not 0, because it is charged now, right? So this is obviously pretty simple, right? So yeah, now we'll talk about discharging of a capacitor. Right? Suppose initially a capacitor has a charge E into C. It is fully charged, right? I can, for this circuit, let's say it is connected to a resistance R and it is discharging itself. This is a capacitor of capacitance C. right? Now it is getting discharged. So again, I can apply the loop rule and write Q by C plus IR. The potentials across these two components will be 0, right? And this I can write as dq by q is equals to minus 1 by rc dt, because I is equals to dq by dt. So I'll obtain q is equals to q naught, which is ec, into e raised to minus t by rc, which is the equation for discharging of the capacitor. Now I is dq by dt, I know that. So I can simply substitute and find this I naught my e raised to minus t by rc. Since it is discharging, the current is negative, and I naught is minus e by r. Right. So I come to a very important point now. A fully charged capacitor acts like an open circuit, right? So this brings us to the end of the theory for the chapter current electricity. Next we move on to a few questions, a few important questions we'll be seeing from this chapter, especially from the JEE point of view or other competitive examinations point of view. So this chapter introduces a very new concept to the flow of charges, and it is quite important from examination point of view and otherwise as well, especially if you're planning to pursue a career in electronics, right? It discusses the very fundamentals of current electricity. Thank you so much, guys. Let's move on to the questions.